Okay, I'm going to break the rules a little bit on this one because it asks us to use a pencil to plot the graph, but I'm going to use a marker because it shows up a bit better in the video. And I'm also not going to do each one in the order that they're provided. Instead, I'm going to do C here because it's close to the x-axis, and then we'll just see how the other ones kind of extend from that, because you'll see that they all have the same, they're all parabolas, they all have the same horizontal stretch to the right 3, but they all have different vertical stretches. And so the point of the problem is to see how these kind of all affect or mesh together. So using C, we have a shift right 3 and a shift down 1, which would put the point right there at 3 comma negative 1. And then we have to plot at least 7 other points. So we'll go 3 to the right and 3 to the left. So if I were to replace x with 4 minus 3 squared is 1. 1 minus 1 is 0. Replace with 5 would be 4 minus 1, which is 3. And then to replace with 6 would give me 9 minus 1, which is 8. So there are the 3 points I would get on this side. And by symmetry for the parabola, we'd have the same point over here. And then we would shift 1, 2, 3 up to there. And then we would get the 0, 8. So those would be the points on the parabola. And then it says, at each point you made, use a pen to draw a tangent line that was about 1 centimeter long. So we'll do that in green. So of course down here at the bottom, the tangent line would be horizontal. And then as we move this direction, the tangent line would become more and more positively sloped, right? So there's one tangent line, there's another tangent line, and then finally there's a final tangent line on the right hand side. And then on the left, the tangent lines would look like the same thing, but again symmetric. So that way, a little bit steeper, and then a little bit steeper. So those would be 1 centimeter long tangent lines at every one of those points. Now, for the rest of the parts, it just has us draw the exact same parabola, but shifted with different vertical shifts. So for example, this one would be shifted up 3 from that one. So it'd be 1, 2, 3, 1, 2, 3, whoops, 1, 2, 3, 1, 2, 3. This one's going to go off the board, and then here, and then 1, 2, 3, and off the board. And again, the tangent lines would look identical, right? This one would be about here, there, 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 and there. And then for parts A and B, where the shifts are now, let's see, down 8 from the parent function and down 5 from the parent function, those would be starting at 3 comma negative 8 and 3 comma negative 5. But the general shape is going to be the same, right? Like that and like that and like that, and then it's going to go 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3, 1, 2, 3, 4, 5, and similarly down here. So already went up 1, so now 3, etc. And we don't really need to put them all in. We're starting to get the idea here. Right here, the tangent lines are always this way. Here, they're always there. It's steeper and steeper. And so the point of these problems are that with whatever the shape is, you can always see what the different tangent lines look like to the underlying curve. But we only did them with dots and with 1 centimeter lines. So for each of the equations above, can we actually determine what dy dx is and what dy dx is evaluated at 4? So notice that all of these equations are just y equals x minus 3 squared plus various constants. So dy dx is simply 2 times x minus 3. The constant's derivative is, of course, 0. And so the dy dx evaluated at x equals 4 is going to provide 4 minus 3, which is 1. 2 times 1 is 2. So when you evaluate it at 4, you get 2. So what's happening is that every one of these lines has a slope that is 2, because regardless of where you were on this vertical line at x equals 4, for all of these curves, you can see that the tangent line slope is exactly the same, and that value happens to be 2. Okay, and this is the beginning of my idea of what is a slope field. So here we have drawing a slope field for various differential equations. It says to do 1, 2, 3, 6, but I think I'm going to do 2, 3, 6 to give us a general idea of what's going on, and then you can do the other ones for your classwork, for your homework. So in this particular one, it says 2y equals 0. So if we were to let y equal 0, y equaling 0 would be anything here. 2 times 0 would be 0. So let me do this in a different color other than black so it shows up. So all of these points located at 0, 0, 1, 0, 2, 0, 3, 0, etc. are always going to give you a value here where you let y equal 0, and thus you get a slope of 0. At y equals 1, any point on this line, 2 times 1 is equal to 2. So at these points we'd be expecting some slope 2. I tried to make those look like they're slope 2. They're almost looking like slope 1 now. But I'll make it more dramatic in the next one, because any point along this horizontal level here where y is equal to 2, 2 times 2 would be equal to 4. So we need to make these sharper. So there, hopefully, it's noticeable that I am definitely at one level here, and then I became sharper up here. Down here, where y equals -1, 2 times -1 is -2. So I'm going to try to draw it about the same level as this one, although this was supposed to be 2. So -2 would just be the same sort of level, but in a negative direction. And similarly, by the time you get to the y equals -2, that should be -4, which is again negative, but steeper than the ones above. So those would look something like that. So that's the general way that we fill in all of the points of a slope field. So let's try 3 as promised. Now 3 is a little bit more dramatic, right? It has to take the x and the y values in, trying to figure out what you get out of those. So again, let's use the same idea. If I stick in 0, 0, I get 0. But this time if I stick in 1, 0, I actually get a slope of 1. And if I stick in 2, 0, I get a slope of 2. And 3, 0. So I have to make them look like they're getting sharper the further I go this way. On this side, -1 plus 0 would be a -1 slope. -2 plus 0 is sharper in a negative direction, and -3, 0 is even sharper. Okay. How about if we came to here now? So 1, 0, 1 would provide a slope of 1. 1, 1 would provide a slope of 2. 2, 1 would be 3, and 3, 1 would be 4. On this side, -1, -1, 1 would give me 0, and then we get a -1, and then we get a -2. Up here, 0, 2 gives me a slope of 2, and then 1 plus 2 is 3, and then 4, and then 5, so we're getting sharper and sharper and sharper this way. Over here, -1, 2 provides 1, -2, 2 gives me 0, and then -3, 2 gives me -1. So here the interesting pattern I'm seeing is on the line y equals -x, well, if x is the opposite of y, we keep on getting zeros. And then on this way, they keep getting more and more positive, and on this side, they become more and more sharper negative. So I'm just going to complete this by putting in these points. Sharper and sharper negative, and then sharper positive. So that's what the slope field would look like for x plus y. Finally, for 6, we have some quotients going on, so that's going to be a little bit more interesting even, right? 0, 0, well 0 over 0 is indeterminate, so we won't do that one. But if we were to do 1, 0, where x equals 1 and y equals 0, we get a slope of 0. And in fact, anything that has a y of 0 is going to be 0, except for the 0 over 0. But interestingly, if we were to let x equal 0, this is going to become undefined, right? 5 over 0, 3 over 0, undefined in the sense that it's infinite. So those are going to be vertical tangent lines, right? A number over 0 is undefined vertical line. For the other points, let's try 1, 1. 1 and 1 would provide negative 1. Let's see, 2 and 1 would provide negative 1/2, so that's less steep. And then 1, 3, or 3, 1 would provide negative 1/3, which is even less steep. Over here, a 1 and a negative 1 would be a positive 1, and then less steep, and then less steep. And then if we went up here to 1, 2, 1, 2 would be, let's see, the y is 2, and the x is 1, so that would be a negative 2, and then becoming less steep. And then over here would be a positive, because the y's are, again, they're still negative. The y's are positive, x's are negative, so it's going to look like this. Moving down into this quadrant, we end up getting, let's see, 1, negative 1, which would be y over x. That'd be a positive 1, and then less steep. And then this side would be like this. And then over here would be 1, negative 2, which would be 2, so it's going to be steeper and then less steep. Steeper and less steep. So this time we're getting a totally different shape. So these are in general called the slope fields. So now how can we use these? Well, remember when I was graphing these all the way back to that parabola, once we have a slope field, it represents a particular graph. So let's look at this and try to figure out which of these curves could represent which of these functions. Okay, let's just try, let's say, every other one, 7, 12, 9, and 14. 7, 12, 9, and 14. So what solving this process effectively does is, can you figure out which of these graphs are potentially y equals 1? So y equals 1 is a horizontal line. So we're looking for a graph of a horizontal line. That's going to be D. D is the slope field representing y equals 1. In the mind, it looks not like it's many different horizontal lines here, but remember, the slope field is the dy dx, and if y equals 1, dy dx equals 0, which just means your slopes are always 0. For 12, we need to figure out where y equals sine of x. So sine of x is the function that starts at the origin, looks like this. So do we see any graphs or slope fields that look like that? This one's tempting, but I think that's the cosine graph, right? Because it's coming like this. Oh, there's the sine curve over here at E, right? And E, an indicator would be, there's our sine-like curve going through there. So that's E. For 9, y equals x squared, we want the parabola shape. So that's definitely going to be C here. C is where we see the parabola shape. So y equals x squared would be filled in with C. And then finally, 14 is asking for the ln of an absolute value. So remember, ln of x looks like this. So the ln of the absolute value of x is going to give it the symmetry over the y-axis. And that looks like it is there in graph G, right? Graph G is the one that's indicating there. And so that would be the answer to 14. So figuring out which slope field represents which function, y, means looking at the slope field and trying to see what is the underlying curve that is being represented by these 1 centimeter lines, or these short little lines in the slope field. Okay, this is distinct from matching a slope field with a differential equation. Matching a slope field with a differential equation means that you need to figure out which one of the differential equations is being modeled by the slope field. So let's do 17 and 16 on this one. So the way I like to approach this is I usually like to solve for 0. So when I get an x minus y, I ask myself, when does that equal 0? And of course that happens when y equals x. So what I'll do is I'll look through the pictures to see which picture on the line y equals x seems to have some slope 0 type lines. Now this isn't exactly right because it's a little bit off from the exact points 1, 1 and 2, 2 and 3, 3. But notice that it's better than any of these other ones. Those slopes, the slope at 1, 1 is not 0. Here the slope at 1, 1 is not 0. And here the slope at 1, 1 is almost it looks like a negative number. So 17 is going to match with C. Okay, so how about 16? 16 says the derivative of y with respect to x only depends on y. So that means that every horizontal line, which has a particular y, is always going to have the exact same slope. So this time you're looking for a slope field where every horizontal line provides the exact same slope. And so that's definitely going to be answer choice D here, right? D. You can even tell that this is matching correctly because the slopes up here are positive because y is positive, and down here the slopes are negative because y is negative. Okay, so how could we apply this to a different type of problem? Like, here's the slope field for a particular differential equation given as dy dx equals xy. Sketch the solution that goes through 0, 1. So to sketch the solution that goes through a particular point, I'll go to 0, 1, and then I will use the tangent lines, right, these little slopes, the slope field, to tell me which direction that particle would move. So if it moved a little bit to the right, it would start coming upward. And if it were a little bit to the left, it would end up coming in downward. So that's what my curve will generally look like. That's the one that went through the point 0, 1. If we had instead gone through 0, -1, which is located right here, means I can draw a totally different solution starting on a different initial condition. Over here, my slope would force me to come down, and over here, my slope would force me to come down also. So depending on where you start, here it looks like you're getting some kind of shape that's generally, like if I had to give it a shot right here, I'd say it's parabola-like right off the bat, right? Although, in order to find the solution, it would be a different type of problem. Okay, one more for our lesson today, which is one of the slope fields is given, representing dy dx of sine of x plus y, and the other one is dy dx equals sine of x minus y. So in order to do these, I'm going to use the same process I did before. I like to personally figure out that x minus y equals 0 when y equals x. And I know that sine of 0 is 0. So I am looking for a curve, or a slope field, on which the line y equals x seems to provide horizontal tangent lines. This seems to be the curve that would correspond to sine of x minus y. So I'd say B is dy dx equals sine of x minus y. And let's see if that same logic is consistent with the other side. When does x plus y equal 0? Well, x plus y equals 0 when y equals negative x. Sine of 0 is, of course, 0. So here I'd be looking for along the line y equals negative x, am I getting tangent lines that are about horizontal? And the answer is yes. So it seems like A is sine of x plus y. And so that's generally how we work through these problems. So your homework for today is to complete the problems in the packet that we did not complete here on the video.